All right, so I'm bored of writing pi1 of the hyperbolic. So let's make this definition and have some terminology. A Kleinian group is a discrete subgroup of PSL2C. So today I'm going to focus on various of the conjectures that we've seen and hinted at, and I'll make them more precise. And all of these conjectures, and maybe another one that we haven't seen, but it's sort of been implicit in things we've said, all of these will have the feature of some kind of a mystery group that's so mysterious we don't even have possible examples, which I pointed out, is actually a Kleinian group. And it also turns out that because of the structure of these groups and free-manifold topology, if you know your group is a Kleinian group, so for example, if you have a hyperbolic group and its boundary is a two-sphere, if it's going to act discretely on PSL2C, it's going to do that co-compactly. You can't have any other kind of action that's discrete on PSL2C. Okay. But all the conjectures, the conclusion is going to be such and such is a Kleinian group or virtually a Kleinian. So let me write some conjectures from this board. So this is a conjecture we've already seen, I claim, and called the Cannon Conjecture. Gamma hyperbolic, and the boundary of gamma is homeomorphic to S2, then gamma is virtually. So again, as we saw yesterday, it may not act faithfully on the boundary, it may act with finite kernel on the boundary. That's where the virtual comes from. In a sense. If it acted effectively on the boundary, the conjecture would be Kleinian. I guess I'm ignoring orientation issues, so we might also need to pass the H2 number to make it. Okay, so great. So that's a conjecture, and we spent a long time yesterday talking about that. On Tuesday, I said, if you want to understand this conjecture of wall, and you want to do it from a sort of three-manifoldy point of view, JSJ, idea of geometric decomposition, etc., then in order to understand the wall conjecture, you want to understand two things. A, toroidal implies hyperbolic. Hyperbolic there in the sense of Gromov hyperbolic. And hyperbolic implies Kleinian. So this is the case of where the decomposition that I stated on Tuesday is trivial. It's just a single vertex group that has no z-squared subgroup that's atoroidal, conjecture hyperbolic. Okay, but that's wide open. And then once it's word hyperbolic, the conjecture then, according to Cannon, is that it's Kleinian. So what I want to spend the beginning of today doing is making precise the relative version of this conjecture, which is what's going to happen when you do get a non-trivial graph of groups decomposition from your PD3 group, and there are some atoroidal pieces that you are hoping are hyperbolic pieces of the geometric decomposition of the three-manifold. Those are not things whose groups are word hyperbolic. They're supposed to be the fundamental groups of finite volume hyperbolic three-manifolds. The z-squared subgroups could correspond to the tori occurring in the cusps that Nathan talked about in his class. So those are z-squared subgroups. So you're not hyperbolic. So what are you? You're what's called relatively hyperbolic. So in the theme of spectacular mistiming, here's a 6.5-minute crash course in relatively hyperbolic. Okay, so G a group, gamma a group, and P family of subgroups of gamma. So then gamma P is relatively hyperbolic. So this is a notion of not just a group, but a group pair, a group and a collection of subgroups. The thing to have in mind here is the fundamental group of a finite volume hyperbolic three-manifold, and the family P will be the family of z-squared subgroups coming from the cusps in the orientable. Okay, so that's sort of the gold standard example of a relatively hyperbolic pair. There is proper isometric action of gamma on delta hyperbolic space X. Here you should be thinking that X is hyperbolic free space with some, so that some things happen. Now, if I take my finite volume hyperbolic 3 manifold and I make it act on H3 in its discrete and faithful way, the quotient will have finitely many cusps, as Nathan said, and those look like spikes if you stand from far away, and some compact piece in the middle. So there's a compact chunk and finitely many spikes heading out to infinity. So that's the first thing you want from this condition here. So when I take X and I factor out the gamma action, this should be quasi-isometric to a wedge of some rays, where I'm wedging at the point 0. So after quasi-isometry, it doesn't matter where you wedge. And how many of them? One for each element of P. Okay. So that's what the quotient looks like. Now, this is not enough to get a relatively hyperbolic action. You need to put some extra condition on it. The z-squared subgroups of the finite volume hyperbolic 3 manifold acting on H3 have a fixed point, and they're acting by parabolic isometry. So P here stands for parabolic, and you need to insist that that's the case here. So there's a second condition here, and that says for each ray, so let's call this R sub P, so it's a ray indexed by an element of my peripheral family in this quotient. There is a lift of R sub P to R sub P tilde in X. Okay, so that's a geodesic ray in X. If we wanted a geodesic, you could have taken a shortcut downstairs. A geodesic has to lift to a geodesic. So that the array in the hyperbolic space, remember, gives an equivalence class of rays, which gives a point on the boundary, so that P fixes the point on boundary gamma, or boundary X, sorry, boundary X, not the boundary gamma, it's the boundary of this hyperbolic space, associated to this lift. And also, now I'm going to say some words and not say what they mean. Basically, I needed to act parabolic, so fixing horospheres. So also coarsely preserves sub-level sets of so horoballs is preserving of the associated Boozerman function. Okay, so I'll draw a picture to sort of indicate what this Boozerman function means. I have a ray going out to infinity. So this is maybe C sub P, which is, and this is the ray R sub P tilde. Okay, so I take so what's a sub-level set of a Boozerman function? Well, I'm trying to measure how close I am to this point at infinity. But the answer is I'm infinitely far away. So that's not good. Instead, I can measure a relative distance to the boundary. So I take some element P in the group and I hit the ray with that element P in the group, and I get this asymptotic ray. It goes like this. All right, so these rays eventually become very, very, very close together. So I can parameterize these rays so that this time is the same time on this ray as on this ray. And now I can ask whether a point on this ray and a point on this ray are relatively closer to the boundary or not by pushing them forward the same distance and seeing where they end up relative to the other on the line. So that's basically, so a choice of such function, which is a choice of time 0 on one ray, gives a Boozerman function. And I want this to be preserving that relative distance to the boundary, which is exactly what happens for a parabolic isometry. So in the upper half space, the point at infinity, the horoball is the point above some fixed horizontal plane, and this sub-level set of the Boozerman function is exactly this plane. And the region above it. The level set of the Boozerman function is the plane, the sub-level set is the bit above. So it's exactly the parabolas. The coarsening of that. And the coarsely preserved is because deltas you have to add up and suddenly the approximate. This is only coarsely well defined. So there's this second technical condition that you need. And I don't know, for the experts who already know this, but I'll say the words anyway. If you only insist on this, you could get things like degenerate ends of hyperbolic free manifolds and other such things. You could be acting as a fiber on some built hyperbolic space. You're working coarsely aligned, and you're not doing a relatively hyperbolic thing. Okay. So you need this extra acting parabolically type condition. All right, great. So that's relatively hyperbolic groups. And they're a way of seeing a generalization of hyperbolic groups to capture subgroups that can't be in hyperbolic groups. But somehow the geometry of the subgroups P is arranged in a hyperbolic-like fashion. And if you kill their geometry by making them lie on level sets of chorospheres and then warping the metric like you do on a Horror ball, then you get something negatively curved. Okay, so this definition is due to Gromov. Other definitions of relatively hyperbolic, Farb had a different definition. Bowditch had two definitions, one of which is obviously this one, and the other of which is obviously Farb's. Both proved that his were the same. There's the definitions of Ozen, all the definitions are the same, but careful, if you read Farb's paper, you need relatively hyperbolic plus bounded coset penetration. So here's a weaker notion and then adds an extra condition that this definition is Gromov's original definition. Okay, right. Okay, so here's my second conjecture. And then I'll explain how this is, I'm going to call this relative canon. And I'll explain how it relates to PD3 groups and so on. So if gamma P is relatively hyperbolic, RH, and elements of P are all Z squareds. And, oh, I forgot to say, so there's this X here. There's a Gromov boundary of X because it's a hyperbolic space. And turns out that the space X is not even well defined up to quasi-isometry. But the boundary of X is well defined up to homeomorphism just by the pair G and T. Any other X upon which this acts will have the same Gromov boundary, although it may have a not quasi-isometric X. Okay, but nonetheless, this is determined just by the pair G and P, and that's the notation system. I don't know why G wants to be a group today. And this is called the Bowditch boundary, usually. Although, as you can see, it's implicit in Gromov's definition. Gromov certainly didn't prove, for example, this claim that the boundary doesn't depend. All right, so then that's the boundary we want to think about. The boundary with respect to P of gamma, and that should be L2. And gamma is plane. Gamma is plane. Having these Z-squares here as parabolics forces the group gamma to act faithfully in its boundary, and then the correct conjecture is plane. All right, so great. These are the sorts of things that I would conjecture the appropriate atoroidal implies hyperbolic conjecture in the case of these atoroidal pieces of the JFJ that are actual, when they're actual edges. The atoroidal implies hyperbolic should be that you get things that look like that, relatively hyperbolic in two-sphere boundary. So why two-sphere boundary? I was going to explain that. So first, in general, if P is in P and CP in this boundary, the gamma is fixed by P, it's going to fix a unique point. I'm going to implicitly assume here that the elements of P are all infinite, and otherwise you might have some constraints. But if it's infinite, it's fixed by a unique point. And P acts properly and co-compactly by homeomorphisms on the boundary minus this point that's fixed. Okay, so here again, you should be thinking about hyperbolic free space. Your z-squared subgroup acts fixing the point at infinity. It stabilizes the plane. It also stabilizes the real plane, the bottom of the hyperbolic space, the boundary minus the point at infinity, and the z-squared just acts in the standard way. When you turn the plane union a point at infinity into the Riemann sphere, you maybe did not do that in an isometric way, so now it's just acting by homeomorphisms. If you're careful, there are ways of putting metrics on this coming from Boozman functions that make this an isometric action. But actually, this is the thing. So in case our boundary is equal to, we remove a point and the parabolic subgroups act properly and co-compactly by homeomorphisms on the plane. Well, if there's z-squareds, that's fine, but there are lots of other groups that do that as well. In case the boundary homeomorphic to the two-sphere elements, and the boundary being a homeomorphic to a two-sphere forces the parabolics to be infinite and do this. Elements of P are either virtually z-squared or virtually pi1 of a closed hyperbolic surface, virtually co-compact Fuchsian. So you might reasonably ask, well, what about these? Can't they arise? And the answer is absolutely, they can arise. So parabolics like this arise from pi1 of a compact hyperbolic Green manifold with totally geodesic boundary. Now that boundary is the boundary of the manifold. Okay. So if you do that, you might get a group that's relatively hyperbolic relative to a high edge in the surface group. That boundary is going to be a two-sphere. That's not the boundary of H3. That's not the limit set of the action on H3 that might come from putting such a hyperbolic structure on that. That limit set on H3 of this thing is going to be a Sierpinski carpet instead. The totally geodesic boundary, those don't act parabolically. Those act properly and discontinuously on its domain of discontinuity, which is the disk at infinity, and that disk is missing from the limit set. So you remove a whole bunch of disks from the sphere, and you get a Sierpinski carpet, and that will be the limit set of this thing as long as it stays. And then when you make those parabolics, you crush those circles to points, and then the quotient of the Sierpinski carpet by crushing each peripheral circle to a different point is just it. And that's how you see the boundary. And that's a general procedure that can work. So there might be lots of ways in which a group can be hyperbolic relative to subgroups, different subgroups. So in this case, this group is a hyperbolic group. And it has a perfectly good boundary, and that perfectly good boundary is a Sierpinski carpet. It's also a relatively hyperbolic group relative to a surface group, and then it has a boundary that's a two-scale.
Does mean we can change conjecture to include themselves?
Hold on. Hold on. Wait. There's going to be a conjecture 3. We're falling on board. But I'm going to finish saying something. So there are, of course, cases where this thing could have some totally geodesic boundary, but also not be compact, but have some cusps. And then some parabolics will be z-squared, and some will be higher surfaces. That can totally arise. I'm going to not talk about those kinds of things today. Those would be relatively hyperbolic groups whose natural boundary, so you can always throw away the hyperbolic groups that occur in P, and you'll still be relatively hyperbolic. So if you do that in those cases, you'll have a relatively hyperbolic group with z-squared parabolics and a Sierpinski carpet limits boundary. And I'm going to ignore those today. Don't ask me about those anymore. There'll be a conjecture about these sorts of groups, and it's the one that Mia thinks it is. Okay. But first, let's bring this back to the Poincare duality setting. So here's a theorem. Could be earlier than this, but it's been written down in 2 papers like that are written by these people, Manning Wong and Shiku Walsh. And here I really want to add the Damani, because sort of what he did was key to this. He sort of did a relatively hyperbolic version of S being a mess, but that doesn't happen on the Bowditch boundary. It happens on the Damani boundary. If you can do such a thing. Okay, so if I remember, we're interested in Poincare duality groups, so those had better be torsion free. You don't have a chance of your homological finiteness condition. And you're relatively hyperbolic, then the Bowditch boundary is homeomorphic to a two-sphere if and only if you're a PD3 pair. Okay, the double along the peripheral subgroups. You now have to double them all of them, not just the one. So this is a slight generalization of the definition I gave on Tuesday, but it's still the right definition. And now you'll get a new group. That'll be a relatively hyperbolic group. If you double this guy, it'll be hyperbolic. If you double along the cusps, you're not getting a clanging group.
What do you mean, doubling along the function?
I just mean taking a graph of groups with vertex groups corresponding to groups and edge groups corresponding to P's and gluing by the identity. Yeah. So that's the definition of a PD3 pair, is that doubling gives you a PD3 group. And that's equivalent to a homological definition. And we'll talk about that briefly on Tuesday. Okay, so
non-empty or
well, if P is empty, then this is the Besvina mess theorem I talked about on Tuesday. A hyperbolic group, torsion-free hyperbolic group has two-sphere boundary if and only if it's a PD3 group. So gamma, comma, empty set is a PD3 pair if and only if gamma is already a PD3 group. So this you can. I'm in this conjecture. I'm assuming P is non-empty because otherwise with this conjecture. So let's write here P not empty because otherwise I might say some wrong things because I'll secretly be thinking about Cannon Conjecture or not thinking of whatever. Okay, so. Let me just briefly talk about. Okay, Neil wanted me to adapt this conjecture to. Let's suppose here's a theorem. If Papovich and Kleiner says if gamma is a hyperbolic group and boundary of gamma is the Sierpinski carpet. Okay, so now this is a hyperbolic group, but I said this kind of behavior can also arise from a relatively hyperbolic group with two-sphere boundary. And they find that family. So there exists a family P of, well, subgroups, subgroups of gamma which are hyperbolic. I think this is probably the quickest way to say it. Hyperbolic with S1 boundary. And remember, we spent some time understanding what those groups are yesterday. Family P of subgroups, hyperbolic with S1 boundary. So some things happen. Gamma P is relatively hyperbolic. So then we're in this setting. Well, two, well, I'll just say gamma P is a hyperbolic. Yeah, so the PD3 pair. So the Bowditch boundary is two-sphere and so on and so forth. They also prove that if you do this doubling construction where we know we're going to get a PD3 group, this double is actually a hyperbolic group, so it has two-sphere boundary. So here's a conjecture that they make. So I'll call it today the KK conjecture. I sometimes say this is the carpet conjecture. So gamma hyperbolic boundary of gamma is instant carpet. The gamma is vertically defined. And again, there's an issue about acting faithful in the boundary.
In the theorem, is the collection of subgroups unique?
Yeah, Yeah, they correspond to stabilizers of orbits of the peripheral circles, and they prove there are finitely many orbits of those. Each one of those is stabilized by a full thing acting as a hyperbolic group with that circle as its boundary, and that's the. So it's a unique up to conjugation. This is you should think of as conjugative representatives of stabilizers, and so this the up to conjugation and reordering. It's unique. Yeah. And they come exactly from the peripheral circle of the Sierpinski carpet. So here's a corollary due to Kapovich and Kleiner. Okay, so you take this group here, you double, you have a PD3 pair, you double it, you get a hyperbolic group that has two-sphere boundary. So if you knew the Cannon conjecture, the double would be Kleinian, but a subgroup of a Kleinian group is obviously Kleinian, so this would be Kleinian. So Kapovich and Kleiner proved that conjecture 1 implies conjecture 3. I'm going to spend 10 seconds looking at my notes to see where I'm what I've got. Oh yeah, that's the other thing I wanted to mention about these groups here. So yesterday we talked about a criteria of Markovich, and I said also Hazinski about when a group to a boundary was Kleinian in terms of being virtually compact special, and Hazinski, I think I said 15 words, but it's worth recording, proved a similar thing for groups with a carpet boundary. In fact, groups with a planar boundary, that's some issues with two of them. So gamma is hyperbolic. Boundary of gamma has a carpet, and gamma is virtually compact special. Then gamma is virtually fine. Does it go by Atelier? No, it doesn't. Maybe it does. It certainly could. Yeah. Yeah. So. As David pointed out, yeah, there's a proof of this which is morally pretty short, but involves hitting things with a gigantic hammer. Double it, and you get a group with two-sphere boundary, but that has a splitting over quasi-convex subgroups. And then being virtually compact special means you virtually have this quasi-convex hierarchy, and then Danny's massive work would show that the double was cubulated. And then Markovich or Hazinski would show that the whole thing was cubulated, and then this would be a quasi-convex subject which was cubulated. That's not good. That might be a proof. I don't remember. I mean, I was more on top of the two-sphere case.
So the three complex gives you basically distance equation for the Martin hierarchy.
Yeah, I mean, this is sort of what I was talking about yesterday. That's what Markovich is sort of doing. Except he. Well, I was just indicating you can derive this from Weis's quasi-convex hierarchy theorem and Markovich's theorem fairly easily. I did see 30 things on the boundary with conformal analysis. But he actually has a different proof of Markovich. He does use it. Okay, great. Okay, so I have some 20 something minutes left. And it's my mini course. So I'm going to indulge myself, and I'm going to spend the rest of the time talking about some of my results. That have something to do with some of these things. So make of that as you look, what you want. So here are three theorems. The first one I proved with Mason Manning and Alex Sister. And we proved that conjecture 1 implies, here's another theorem, this is about 2019, I should prove it. Here's another theorem I proved with Jason, which is sort of an analog of this and Markovich's criteria in the relatively hyperbolic setting. So gamma P relatively hyperbolic, boundary P with gamma two-sphere, as we like. P all is squared, and I'll show you why That's important here. I've thrown away the higher genus things, but you guys figured out floor German, so you can imagine your parabolic subgroups actually come from Euclidean two orthofolds rather than z-squareds. I don't like those. Well, maybe we'll see where this comes in because it's pretty later. But this, well, before I finish there, this is the key case that you need for attacking the Ball's conjecture the way I suggested on Tuesday. So I really think this is an important case of what's maybe the more natural, relatively hyperbolic version. All right. And then if gamma is virtually compact special, then gamma is tiny. And again, actually not virtually. And then here's a third theorem that's almost written. Not quite finished. So here I proved this with Kaczynski, Manning, and Yamasada, and Alex Sisto, and Genevieve Walsh. Even in our okay, and we proved the following theorem. Conjecture 2 implies conjecture 1 in the residually finite case. Okay, so what do I mean by that? If conjecture 2 is true, and we have a residually finite hyperbolic group with two-sphere boundary, then that residually finite hyperbolic with the two-sphere boundary is virtually fine. So extra hypothesis, definitely not known already whether all hyperbolic groups are residually finite. Doesn't help, I don't think, as far as I know, to assume your hyperbolic group is a PD3 group, still don't know if it's residually finite. If we add that hypothesis, then we can derive conjecture 1 and conjecture 2. I'm not going to talk about this conjecture, so Genevieve will talk about this next Thursday. Walsh Thursday. I'll just say was drilling and leave it at that. But I claim that this is, I really like, I'm really happy with this theorem. We work hard to prove that I like to prove. This is the better direction, I think. And why do I think that? Well, from the point of view of free manifolds, things with boundary are always Haken. Okay. If you were Haken in the hyperbolic case, that might mean you could split as a graph of groups. If that happened to be a quasi-convex splitting, then you might reduce conjecture 1 to conjecture 3. So conjecture 2 and conjecture 3 are really about Haken things. And the proof of the geometrization theorem in the Haken case, at least in the aspherical case, that's the sort of thing that has some things that look like geometric group theory in it. The proof by Perelman in the non-Haken case does not, as far as I can tell. If anyone knows how to do Ricci flow on hyperbolic groups, then please come and talk to me and we'll see what happens. But I don't have any idea. So I think Haken, so historically Haken 3 manifolds were easier to understand. And conjecture 2 and conjecture 3 should really be about Haken things in some sense. I'm not going to elaborate on that anymore. Okay. So what I wanted to do is give the briefest sketch of theorems A and B. Very brief. Maybe a good flavor of what's going on. So in both cases, we have gamma P relatively hyperbolic, and let's say P equals P1 through Pn, some finite collection. Maybe you should have said P is finite. In my setting. Finite collection and Pi, maybe it's generated by AI and BI, and that's isomorphic to Z squared. So we have these Z squared subgroups. And the boundaries are 2 set. So maybe I'll write that up just so that we remember. Okay, so here's a theorem. Here's a theorem with Jason from a long time ago, independently proved by Ozen. there exists finite f contained in gamma. So that for any gamma 1 through gamma n, gamma I in Pi, but not in F, the quotient of G by the normal closure of the sets gamma I is hyperbolic. It hasn't come up yet this week, but this is a group theoretic analog in some sense of a classic or three-manifold theorem of Thurston called the hyperbolic Dane surgery or hyperbolic Dane filling theorem. In the three-manifold setting, these z-squareds are tori, and you could take this boundary torus and glue on a solid torus. And Van Kampen's theorem says on that z-squared, you're turning that z-squared into a z, which you do by killing the element that bounds a disk in the solid torus. And then Van Kampen's theorem applied to the whole group with these tori says that this is the fundamental group of the quotient. And Thurston says as long as you avoid finitely many bad slopes on each torus, then the resulting thing is a real hyperbolic three-manifold. And one of the lightning talks, I think yesterday we saw something a long, very quick, long list of Sixth theorem and so on, which were other generalizations of that. This is a sort of a group theoretic generalization. Yeah. We're in the context of conjecture 2 and theorem B with all z squares. Yeah, so I'm taking these z squares, I'm killing some element, as z squares become z's. The content is that you don't kill anything extra than you expected, and you end up with a hyperbolic group. Okay. Right. Right. So that's a key ingredient in all of in theorem A and theorem B. It's not at all used in theorem C. All right, here's another theorem. And this is the key thing that we proved in this paper in order to get, I'll show you how this explains this theorem A. Same setting.
So just to be clear about the same setting, this is for general relative hyperbolic groups, but the parabolics are supposed to be this one.
This theorem works for general relatively hyperbolic groups with the peripheral groups being z squared. If the peripheral groups are not z squared, killing other normal subgroups, you'll get a relatively hyperbolic pair. All sorts of things are known. But killing z squareds, you kill the z squared down to a z. The real theorem is you're hyperbolic relative to the images of the z squared. Blah blah blah.
Can you repeat about the version where the parabolics are not assumed to be this well?
Yeah, so take any normal subgroups of the parabolic subgroups, then those quotients of the peripherals by those normal subgroups will inject as long as you avoid these things, and you'll be hyperbolic relative to their images. That's the general relative hyperbolic Dane filling. So, but this is the only one that's going to today. Only for a long time, and you've never seen me talk about that. That's all I do. But also, so that's the S2 boundary is not needed for this theorem, but it is needed for this theorem. Same setting for a larger F, something still finite. Let's call this group something. G bar. The G bar is hyperbolic. The boundary of G bar is a two-sphere. That's not identical obvious. Probably the easiest way to prove this actually is to do a homological argument and prove that the quotient is PD3 group and once it's hyperbolic, it's being an X and so on. So, yeah. But we have a direct argument which is useful for certain other things. All right. We're not there yet. Okay. I found a quotient that is a hyperbolic group with two-sphere boundary. And the Cannon Conjecture says it's Kleinian, but fine, lots of groups now want the Kleinian groups and nothing fine. So we're not done. We have some work to do. But let's prove, I'm going to finish the proofs of theorem A and theorem B simultaneously, because it's the end of the proof is literally the same argument. So I'm gonna stop proving theorem A for a minute and get the extra thing for theorem B. And this is the theorem that we proved in the paper proving this theorem. if gamma is virtually compact special, then for still larger, actually for lots of choices of gamma I, but maybe not all. Yeah, this is this took me up with my hand earlier. For lots of choices of gamma I, as I said, strictly speaking, you have to pass to some finite index subgroup of these squares to make sure they lie in those, which is different than avoiding a finite set. Gammas and G's. Sorry. Gamma bar, this filled thing, is also virtually compact special. Okay, so to finish, we'll finish the theorem, but so at this point, these are virtually compact special quotients, which are hyperbolic with two-sphere boundary. So actually, we already know that those are Kleinian by Markovich's theorem. And so in theorem, so in trying to prove theorem B, we're not conditional on conjecture one. We're in the situation where we assume we're virtually compact special. We get these fillings that are virtually compact special, these quotients that are virtually compact special, and those are Kleinian. It's not a conditional statement. All right, but still, all we know so far is that we suggest a Kleinian group. What do we do? Well, we've got 12 minutes left of my mini course. So I figure it's time to introduce you to two giant new parts of hyperbolic free manifold topology in one little argument. So I apologize for that, but I like this argument, so I'm going to show it to you anyway. Right, so to finish the proofs of theorem A and theorem B, in both cases we have a sequence. We can take a sequence. We can take lots and lots of these fillings, not just one, but we can choose a family of gamma i's that are going up into infinity in Z squared. And here, there's a finite index subgroup, but as long as you take a family of gamma i's that are non-trivial going up into infinity in those Z squared. We got a whole sequence of these things. So we have a sequence, gamma n bar, of Kleinian groups with quotient maps. And I apologize for the G versus gammas. This is just my brain is broken today. I don't know what's wrong. With quotient maps, gamma, every row n. The gamma. Okay. So we actually here in this stage, we're only need that they're Kleinian. But actually, we know that they're co-compact Kleinian. Because they're coming from things with boundaries. So as we heard from Nathan, these are Kleinian groups. Well, by definition, they admit these discrete faithful. The gamma, so this map here, discrete faithful on gamma n bar. Of course, this quotient map, so no longer faithful. Discrete image. But the kernels of these maps are getting sparser and sparser. They're vanishing off to infinity. Okay, so what I'd like to do is take a limit of these representations. So the right thing to do here is to take a limit in the character variety, if it exists. Okay, so there are two cases. One, so let's say we have this tau sub n mapping from gamma into PSL to C. Okay, and that's just this composition here. Okay, it's a sequence of representations, and we can ask if there's a limit. Good question, George?
Yeah. How are you picking the sequence? Like this,
I'm starting here, and now on each of these Z squares, I'm choosing a long sequence of gamma ones, and a sequence of gamma twos, and a sequence of gamma threes, all of which avoid this finite set. And this larger finite set, and if we're trying to prove theorem B, land in some finite index subgroup, and so on. So I'm just applying this theorem infinitely many times for longer and longer gamma i's. I'm making them get longer in each of these squares. In any sense of longer, it's just they're going up to infinity and satisfying the hypotheses of these three theorems.
Are you exhausting these square by finite sets, or you eventually like having to grow to everything?
I'm just choosing a single element, gamma I.
Okay.
And I'm just making sure that goes out for all finite sets. The kernels of all of the maps from gamma to gamma n bar intersect trivial. That's right. Yeah. So and maybe I'll write that the intersection of the n, the kernels of tau n are the trivial groups. Okay. And that's because the kernels go to 1 here, and these are all fake. So the two cases. So tau n converge to some tau. I'm not going to start now telling you what that means. Think, if you like, about after conjugacy matrix coefficients converging. So that's something that could happen. That would be great. This, and then you have to argue, but it's not so hard. Then this will be discrete and faithful. And then we win. All right, what's the other thing that can happen? Well, going back to Morgan and Shalin, the second thing that can happen is that tau n, and I'm really not going to tell you what this means, converge to an action on a real tree, an R tree, an action, a gamma action on an R tree. And then when you have that, there's a machine that you keep in the side of your office, built by the Rips Corporation, that takes as input your action on a real tree and outputs an action on a sequential tree, which is a graph of Rips decomposition. So this would imply gamma splits over a virtually abelian blip in this case. You have to analyze the action on the R subgroup. You have to analyze the action on the R tree, that it does the right things for you. The Rips machine applies, it outputs a simplicial graph of Rips decomposition, edge groups that are abelian and non-trivial. And this doesn't happen. You can see that in lots of ways with homology or with the boundary. So actually, this case doesn't happen. So we're in case 1, does happen, and these must converge to a discrete faithful representation of gamma in the BS1C, which is to say that it's plane.
You don't have to go back and look at the pieces of the JSJ and apply your case 1 again.
Gamma is like a finite volume hyperbolic manifold. There is no JSJ in this case. There's no splittings over Z squared. If you like for homological reasons, but yeah, there's no. This is an atorial thing. Any Z squareds are peripheral and don't give you a graph. Yeah, there's no JSJ. You just can't do this. All right. Right. So that is how you prove these theorems. So I can do two things now. I can stop, or I can do the promised. Here's a list of open questions about Poincare duality groups, which could start the open problem section.
How did you use the contact and special part? So the PSLC came from a conjecture model, right?
Right. So here, Markovich's criterion says if gamma bar is virtually compact special and has Kuskian boundary, then actually we know it's finite. So
I thought you were assuming conjecture.
Right, I proved two theorems simultaneously. The theorem A I assumed conjecture 1. The theorem B I didn't, and instead of using conjecture 1, I used Markovich.
You assumed.
Yeah, so sorry, that was I ran two proofs at the same time in superposition. Yeah, it looked a little blurry.
Backing up a little bit, this average boundary for this history and that was thing about. So essentially, is there a best kind of you made the statement that it's not an I mean it's topologically an invariant, but the fillings are not quasi-isometric feature. Is there a best way to do that, or
in this setting, yes. I mean, the question, the only non-invariance of quasi-isometry, and this was proved by Healy and Bruska, is how you choose to build horrible. So you should just use a single exponential Walton function. And and since Z squared parabolic, so those Horace fields are quasi-isometric horror. So those parabols that you build are quasi-isometric, H2 parabola.
so you could scale faster?
You can scale faster than that, that's right. And then you get non-quasi-isometric parabolas. In particular, if you start with Z squared and you exponentially warp, Then you just have a horror sphere in H3, and that has nice bounded geometry. If you start with z squared and you double exponentially warp, there's more and more volume as you go down, and you don't get bounded geometry. So that's a bad thing to do, but you can do it. Yeah, that's the only how you choose to warp the horrible is the only ambiguity once it shows you that. Yeah. Okay, well, I guess now I'm going to stop.
Hard questions for anyone?
Building,
Speak up.
one question about any building, like, we were talking about the case with the vertical group z squared earlier, so. But, you know, in the incremental setting, there's this. Thing, in terms of that.
Yeah, no, the relatively hyperbolic filling theorem. Oh, did you want for the boundaries to be two sphere or just quotients to be hyperbolic?
Yeah, for the solution to be actually hyperbolic rather than.
Oh, like real hyperbolic. Yeah, I hadn't thought about that. Probably. You could probably do it. Homological argument. So the fact that the quotient is hyperbolic, fine. The homological argument there will actually give you the boundaries of two sphere. And then, yeah.
So what's the way without the curve being x squared, you can say that it's going to the bills and finite set curves.
Oh, well, conditional on conjectures. Yeah. Yeah. I mean, if you're talking about a real hyperbolic thing. Yeah, I mean, so if I had a counterexample to this conjecture, and it had these surface groups, and I did your procedure to that, I think I could prove it was a counterexample to this conjecture. But if I assume this conjecture, then the analog of theorem A would go through in that setting. That's what I'm trying to say. Yeah. The sum set thing. It follows. I think if that didn't work, you would already have had to have started with the counterexample. Something like that would work, but I'm not exactly sure. All right.
If you have a Gromov hyperbolic group with C around it, and you know it has a positive on that surface subgroup, is it known that it has to be the finite?
No, because we could take this guy. Double it. Yeah. So if you knew this conjecture, I think we could probably answer your question. Although it doesn't follow immediately, I think you probably could. But no, this a counterexample to this would be a counterexample. One quasi-convex surface subject gets somewhere, so it gets you into the half of the subsets.
You would use step reporting to actually get into the Hawking situation.
Yeah. Or something else. I think I could prove, maybe modulo which is a 2 for it, that if there was a single quasi-convex surface subgroup and this conjecture were true, then and I don't think I would have to assume separable. But we have to do that.
In the scarcity topic, is this equal to asking about the relatively hyperbolic splitting, say along the surface which is boundary Z? Essentially, something like trying to do a further hierarchy with relative zooming simulation. So, I mean, the way we start,
But you want to find a further surface
yes,
with boundary lines on
boundary
them.
lines on hyperbolic.
Yeah, so that could be something you could try to do. That sounds great. I don't think I guess it's equivalent to that because if you prove that the thing was sliding, then you would know you could do that. But yeah, so I guess it's cool.
In this theorem, you say that if you don't have a bigger finite set, after that, you still have a theorem boundary.
Right.
Is it something special about the two sphere, or can you do you can preserve the same boundary after that?
No, that's very special to the two sphere. And generally, you expect the boundary to change a lot under data. And in fact, I could have, instead of killing these cyclic groups, I could have killed finite index subgroups with G squared, and I still would have got a hyperbolic group as the quotient, and now the boundary would not be a two sphere. it would be some crazy garbage. Yeah, it's very special to this setting where the boundary is a two-sphere and it goes to a two-sphere. And that's sort of related to the fact that we have these hyperbolic finite volume three manifolds and these compact ones, and they both have the same boundary in a different category. And there's this wonderful first hyperbolic filling thing that says that the procedure goes from something in two-sphere boundary to something highly non-obvious how that. It's not, this is not a quotient of the two-sphere you started with. It's much more complicated than that. And in general, you won't expect the boundary to take aside. It's very particular in this situation.
Is there any sense in which if you take finite code and take subgroups which are deep but of finite index and you pass through a limit, the boundaries converge to S2
Yeah. That's explained in this statement. Yeah, it's kind of weird.
Okay, let's thank Daniel for the wonderful minicourse. All the minicourse speakers for the wonderful minicourse of the week, and Dave for organizing the staff for being here and having this wonderful week. Thank you. Let's take a 5-minute break, and then John will share the comments and think about open problems.